So in wireless communication, antenna is a front-end device in all wireless communication system. As shown in this figure, antenna is needed at the transmitter side. As here, this is a symbol used to indicate the antenna. Similarly, at the receiver side also, antenna is needed. So antenna is a very important device in wireless communication system. The antenna radiates electromagnetic signals, and those electromagnetic signals, EM waves, travels in free space and reaches the receiving antenna. And at the receiver, we can extract the signal transmitted from the receiver. So the main this antenna converts in this guided waves into EM waves, and those waves are traveling in the free space and received by the receiver. So the antenna is a very important device in most of in wireless communication system. So they, based on the application, there are different type of antennas are there. See, like this, it may be a ARN antenna. This like a parabolic antenna. This is like a log periodic antenna, microstrip antenna, and this is an array of microstrip antennas. So like this patch, this is a microstrip antenna. This microstrip antenna is configured in the form of a array, so to get a more gain. So like this different type of antennas are there in the application. So it's any one of this can be used as a transmitting antenna or a receiving antenna. See, like this. So there are different type of antennas are there based on the applications. So in your syllabus in the laboratory, we are studying microstrip antenna. So this antenna, microstrip antenna, microstrip antenna we are studying, and we are simulating this microstrip antenna. So once we come across the antenna, we have to study the gain of the antenna and resonant frequency of the antenna, beam width of the antenna, and bandwidth of the antenna. So as we are simulating microstrip antenna, we are calculating all these terms: the gain of the antenna, resonant frequency, beam width, bandwidth, the antenna. So this is mainly there are different type of microstrip antennas are there, and in your syllabus in the laboratory, we are implementing inset fed microstrip antenna. This is inset fed microstrip antenna. This is a microstrip structure. Microstrip structure, there is a rectangular patch is there. So like this is a rectangular patch with a particular length. This is the length of the antenna and width of the antenna. This is a copper material, and that is on a substrate. This is a substrate electric material, and bottom there is a ground plane is there. This is a ground plane. This gray color is a ground plane is there over that substrate with a particular permittivity epsilon r and thickness, and over that this is a copper trace. This is a rectangular shape copper trace, copper structure is there. It has a particular length L and width W here, and this is a feeding structure. This is a feed transmission line to feed the signal to the antenna. This structure is a feed line, and actually the antenna is the patch, rectangular patch antenna. So it is also called rectangular patch antenna with inset fed, because here the structure, the feed line is inserted up to a particular length to the antenna, patch antenna. This is a patch antenna. So here see, like this is a feed line is inserted into the structure up to a particular length that is equal to B. So it is called as a inset fed antenna. So this once the source is connected to the antenna, see, like this, once the source is connected to the antenna, current flows over the structure. Current flows through the structure. The current distribution over the structure is as shown in this figure. So this is a current distribution. Current is maximum at the center of the patch. So this is the center of the patch here. Center of the patch. Maximum current will be there at the center of the patch, and minimum current observes at the end of the patch. This is the end. This is the end of the patch, this is the end of the patch. At the end, the current distribution is minimum here and here. And current is maximum at the center and minimum at the ends here, because it is a open circuit. At a open circuit, current is minimum like this. Okay, current is maximum here. Similarly, the voltage is opposite to this. Opposite to this means voltage is maximum at the edges here and here, and voltage is minimum at the center. Similarly, impedance distribution also. Impedance is the minimum at the center here, center of the patch. As if you measure the impedance at the center, or if you plot the impedance as a function of this length of this is the length of the antenna. If you plot impedance as a function of this length, you will observe impedance is minimum at the center of the patch, and impedance is maximum at the edge, this edge and this edge. So that is here the current distribution is shown by a arrows here. Lesser the arrow size means lesser the current, more the arrow size, that is more current here. So the same the current distribution, voltage distribution, and impedance plot will be look like this. If you plot it as a function of length here, so what we can observe, see, this is a current variation I, current variation high. Current is maximum at the center of the patch here, that is at the center here current is maximum, and it is a minimum at the edges here. But voltage is maximum at the edges, voltage is maximum here, voltage is maximum, but a minimum at the center here. Similarly, impedance variation, this is a impedance variation. Impedance is a minimum at the center, and it is a maximum at the edges here and here. Okay, so this is once the source is connected to the antenna, patch antenna, this current distribution, voltage and impedance variation over the length of this as a function of length of the patch antenna, we can observe like this. And this is a cross-sectional view of this patch antenna. So once this antenna source connected to the antenna, this antenna starts radiating, and that usually that radiation takes place at these edges, that is at the width side here and here. So that radiation takes place from the patch antenna once it is excited. So for the designing this antenna, the design concept for this antenna is, we have to find out width and length of the structure for a given operating frequency. So the question will be like this: design a insert fed rectangular microstrip antenna to operate at a resonant frequency f naught, like a 2.4 gigahertz, using substrate with the parameters epsilon r, like a 2.2, tan delta is a 0.001, and the substrate thickness is a 0.8 mm, and characteristic impedance is a 50 ohm. Okay, this is a specification. So what is the required thing is, antenna, you should design the antenna, it should radiate at a 2.4 gigahertz. That means it should give a maximum radiation at a 2.4 gigahertz, and it should constructed using this substrate. This is a problem will be specified like this. So for this for this specification, we have to design the antenna. It should give a resonant frequency of 2.4 gigahertz. That means it should radiate maximum at this particular frequency. To do that, to obtain that, we should calculate length and width of the patch antenna. This is a patch antenna. We have to calculate this length and width of the antenna. To calculate length and width of the antenna, these are the equations, design equations. Width of the patch is given by this equation, that is W. C is the velocity of light, we have to substitute here. Epsilon r is given in the problem, and f naught is a resonant frequency, you have to substitute. You will be getting width of the patch antenna, that is this width we will be getting. Similarly, effective dielectric constant, because this is a microstrip structure, we should use this effective permittivity. That expression for effective permittivity is this, and here we have a H and W calculated from here. We can substitute in this equation to get the effective permittivity. And from that equation, using effective permittivity, you can get the length of the patch. See, this is the length of the patch. We can obtain this length of the patch using this equation, that is L effective minus 2 into delta L. So here L effective is given by this equation, C divided by 2 F naught into effective permittivity, square root of effective permittivity, that is calculated from here. And c is the velocity of light in the free space. And here is a 2 into delta L. Delta L, it is calculated using this equation. This is the expression for calculating the delta L. So this is delta L by H is equal to this. So to get a value of delta, you multiply this right hand side with a H. We will be getting the value of delta. That should be substituted here to get the overall length of the patch antenna. So this is length of the patch antenna you will be getting. So that is W and L we should get to design the antenna. So this length and width depends upon the resonant frequency, at what frequency we want to operate the antenna. So next, here this is a feed line. This is a feed line we have to connect. Feed line means to excite the antenna, we should connect the signal source. For that, we have to add a port. To add the port, we should connect a feed line like this. This is called as a feed line. It has a particular width here, D. It has a particular width D, that feed line. This is also a microstrip line. It has a particular width D, and there is a that what we are doing in the inset fed. The antenna is a inset fed antenna. So this feed line is inserted into the structure with over a length of B. This is the B here. Okay, actually by doing like this, the impedance of the source usually 50 ohm. Here port, what we are attaching port 50 ohm impedance, and this feed line also 50 ohm impedance. So this feed line must be inserted such that at which because as we saw, impedance is maximum here and here, impedance is 0 at the center, minimum at the center, but at somewhere here the impedance is equal to 50 ohm. See here, somewhere here impedance is 50 ohm. It is minimum here, maximum impedance here and here, but somewhere here the impedance is a 50 ohm. So by at a distance B, the impedance usually here becomes a 50 ohm. So this port has a 50 ohm, feed line has a 50 ohm, here the impedance is a 50 ohm, so all will be matched. That's why this feed line must be inserted into the patch as shown here at a distance B. Then matching will be takes place between the source, feed line and the antenna. Maximum power will be delivered to the antenna. So instead of connecting this feed line to the edge here, instead of connecting to the edge, we are connecting somewhere here to the because for the impedance matching. If we connect here this feed line to here, the impedance will not be equal to 50 ohm. So automatically this feed line and the source will not match to the impedance. So what we have to do, we have to find out a position at which the impedance is 50 ohm. So usually at a distance B, it is equal to 50 ohm here. So 50 ohm impedance, antenna impedance, feed line impedance 50 ohm, source impedance 50 ohm, matching will be there, maximum power will be delivered to the antenna. So this feed line, so we have to find out the value of B here, and this D based on the feed line characteristic impedance, that is a 50 ohm here. So to design this, we should go for this equation. This is the equation to calculate the value of B at which the impedance of this microstrip structure is 50 ohm. You should do this. That is L by pi. L is whatever you calculated from here. This L we have to substitute here. Cos inverse of Z0 by Z1. See this pi is a 3.14. We have to substitute. L is length of the antenna. Z0 is a 50 ohm. Here Z1. Z1 means it is Z0 into square root of Z0 into Zn. Z0 is a 50 ohm here. Zn means it is a impedance at the edge. As I said, there is a impedance at the edge here. Okay, that impedance is a Zn here. This impedance Zn we can calculate using microstrip antenna calculator. See here, ZIN can be calculated using microstrip antenna calculator. Okay, we will see that how to get the value of this ZIN. So this ZIN we have to get from the microstrip antenna calculator, and this Z0 is given in the problem. You have to substitute those two values in this equation to get a value of ZN. That you have to put here. Okay, then we will be getting the value of b. So that length we have to take here, b value. Actually that b value will be coming some approximately, but we should still optimize the value of b. For example, we will be getting here 9.25 something, b value will be 9.25, but if you use a b is equal to 9.25, we may not be getting a maximum radiation. Okay, so we have to optimize the value of b, just increasing the value of b or decreasing the value of b above and below this value b. Okay, to get a optimized radiation from this antenna. So while doing simulations, actually for this problem whatever is given, we got a 9.25, but b if you set a 9.25, maximum radiation we did not find. So what we did is b we optimized by increasing the value of b. We observed when b is equal to 12.5 mm, instead of 9.25, if you keep b is equal to 12.5 mm, we got a maximum radiation from this antenna. Through simulation we can do that. Okay, so by doing so we can take this b I have taken here 12.5 mm. Even from this you can get an approximate value of b, but by properly optimizing this, by little bit increasing this or decreasing this, we can get a maximum radiation by this antenna. So through optimization we found this b value is 12.5 mm. So that we were taken while constructing this microstrip antenna. So this is a design equation for this b, and this d value you can get from microstrip line calculator. Microstrip line calculator, see here, use microstrip line calculator to find the value of d. This you already did in um, uh, previous experiments to find the width of the one, like in a line resonator and ring resonator. Width of the this microstrip line is obtained using a microstrip line calculator. Substitute the parameters, given parameters here, epsilon, thickness and frequency. We will be getting this width of this line, that we have to substitute here. Usually for this particular problem we got that d is equal to 1.5 mm, so we have to take this d 1.5 mm here. Okay, so and using these calculations, we got the length of the antenna is 41.78 mm, and this width is equal to 41.41 mm. Width of, using these equations, length is 41.78 mm and width is equal to 49.41 mm. Again these values we have to use these equations. W calculation is this, effective permittivity, length and delta L. All these calculations we have to do to get the values of length and W. But it is as you know, these equations are little bit lengthy. We can use online calculator to get the values of L and W. So in the online calculator is available. You can go to this online, you give a microstrip antenna calculator. So this is a microstrip antenna calculator, not a microstrip line calculator. So microstrip antenna calculator, so you should take here. So in this microstrip antenna calculator, you go to microstrip patch antenna EM calculator. So this will be available here. This is not a microstrip line calculator, it is a microstrip patch antenna calculator. Here we have to substitute the parameters here, that is 2.2 in the problem it is given, and thickness is 0.8 mm, that is in mm only, and frequency is 2.4 gigahertz. Okay, so this is a synthesize here. So we will be getting here that 41.78 mm and 49.41 mm. So here and as we can see, edge input impedance, it is 144 ohm ZN, that as I said here, this so length of the antenna 41.78 mm, W is a 49.41 mm, and this ZIN here, this is from the microstrip antenna calculator, that ZIN is here, this is the value. So that is ZIN is 144 ohms. Okay, this is the length and this is the width. So you can use this online calculator to get the value of L and W, and also ZIN, that is 144. Edge impedance, this is the edge what is the impedance at the edge of this patch antenna, that is 144 ohms. So that we have to use here to calculate the value of Z1, that you have to substitute here. And the length and width, you can use these equations, but in the examination we have to write these equations, but you can verify using online calculator. Online calculator, we got a L is this, W, and A, this is a here, this is from here to here. So there you should provide a gap from here to here and from here to here. So what we did, we have taken this A, double this value. This is 3.6. We have taken this A distance from here to here is here 3.6 mm. Should not be very less. So we have taken this as a 3.6 mm. Okay, and this is a 34 mm, this is a feed line length. Again by optimization, length of the feed line, see from here to here we have taken C is equal to 34 mm. We can observe here by changing the value of this feed line length, we can reduce this, and we can observe what happens to the radiation from this antenna. Actually through optimization we got for this value C is equal to 34 mm, that is a feed line length equal to 34 mm, we got a maximum radiation from this antenna. So like that, the length width calculator using microstrip antenna calculator, you calculate length and width and ZIN, and but this D must be obtained using microstrip line calculator, that what we did in a line resonator and all. Okay, that is for these parameter we will be getting, it is 1.5 mm, that we have to set. And this usually this feed line length you have to take approximately equal to length of this lambda by 2, greater than lambda by 2 we have taken here this feed line length, and this to accommodate this gap provided between the feed line and the structure, we have taken this 3.6 mm. So this is about this structure design. So make insert fed microstrip antenna, we can design using these design equations. Okay, so you can implement the structure if you know this parameter, all these parameter we can implement this. It is a rectangular structure, you can easily implement that in the AWR tool. Okay, once we implement this structure, we have to here draw the radiation pattern, we have to find out the gain of the antenna, we have to see whether it radiates or not, all those things we have to do in the simulation. So in the simulation tool, that is in the AWR, we have to test whether the antenna is radiating or not. Okay, and also is it radiating exactly at the whether it is radiating at a given frequency or not, and what is the gain of the antenna, all those things we can find out from the simulation tool. So in the simulation tool, to find the radiation, whether it is radiating or not, what we are doing is, first we are plotting the S matrix of this, S parameter of this structure. Okay, so this is a one port structure. Antenna is a one port passive device. Antenna is a one port passive device. There is no other port, only one port is there. One port means only one parameter, S11, only one parameter. Here is a 2 is not there. Okay, it is a radiating into the free space, so it is a one port device, and parameter is only S11 is there. So we have to plot this S11 reflection coefficient. It is also called as reflection coefficient at the input here. So we are feeding the structure here at the input here. We should plot this reflection coefficient. So energy will be transmitted from the source to the structure here. If there is a match here, maximum energy will be given to this antenna. Okay, so we have to test that whether maximum energy will be transferred to this antenna or not. That we have to test. So for testing that, what we have to do, we should plot the S11. We should plot the S1. That is it is a ratio of incident wave to the it is a ratio of incident reflected wave to the incident wave, B1 divided by A1. So this is B1 divided by A1. B1 means reflected wave and A1 is the incident. That we have to plot here, S11 here. So what we are expecting is at the resonant frequency, this parameter S11 must be as less as possible. That is the reflected wave here must be minimum as possible compared with the incident wave. So this S1, if you once we plot here at resonant frequency, this S11 should be as minimum as possible. So this is a plot here, S11 plot here. So we should get this plot the S11, and we are plotting this S11 in terms of decibels here. See here like this is the plot at resonant frequency. We have designed it for 2.4 gigahertz, but there is a small shift in the frequency. You are getting at 2.39. I think this is corresponds to 2.39 gigahertz. We are getting a maximum power delivered to the antenna. See, minimum reflection here, S11 is very less. See, it is in the around 37 dB, 37 38 dB here, 30 minus 38 dB. Minus 38 dB means very less reflection is there. That means most of the power is delivered to the antenna. So what we can come to know, so this is a minimum reflection means maximum power is delivered to the antenna, so automatically it radiates maximum. That we have to draw here. We have to draw this S11, and you should see is it resonating at a, so resonating means wherever we are getting a minimum reflection, that is the resonant frequency. You can observe here. See at 2.4 gigahertz nearly, we have minimum reflection is there, and afterwards what you can observe, it is a reflection start increasing here. This is a increasing. Okay, so like this you can find out a bandwidth here by taking minus 10 dB bandwidth. You can take a bandwidth here 10 dB minus 10 dB bandwidth. What is a F1 F2 find here? F1 you can find, take a difference of F2 minus F1, that gives a 10 dB bandwidth from the reflection plot. That way you can find the bandwidth of this one F2 here minus utter minus 10 dB. Find out what is the frequency here, that is F2. Here is a F1. Take a difference of F2 minus F1, we will be getting the bandwidth here. This is a 3 dB sorry minus 10 dB bandwidth. So we have to plot this reflection plot for this antenna. So we are resonating at a 2.4 gigahertz. We have to see the S11 at above and below the resonant frequency. So we are plotting the one from 2.2 gigahertz to 2.6 gigahertz. Okay, we can see what happens to the reflection above and below the resonant frequency. At the resonant frequency, reflection is very less, see like this, and above it start increasing like this, and below also it start increasing here reflection. That means radiation is lesser at these frequencies, and finally there is no radiation at all here, because this is 0 dB means B1 is equal to A1. That means entire wave reflect back at these frequencies, like for example 2.25 gigahertz here or here, the entire reflection will be there. There is no radiation at all here and here. Radiation takes place only in this region. See here minus 10 dB within this from here to here, F1 to F2, we can get a maximum radiation here. For maximum radiation, at least that reflection must be less than minus 10 dB. See from here what we can observe, this is a minus 10 dB. From this frequency to this frequency, that reflection is lesser than minus 10 dB. So only here in this f1 to f2 it radiates maximum. So like we have to plot this graph. Okay, so this is a S11 only, S1 only we can plot for this structure because it is a one port structure. Similarly, so reflection is lesser at the resonant frequency here. Okay, so why the reflection is lesser? Because there is a impedance match here, impedance match at the resonant frequency only we will be getting matching, because the impedance here changes as a function of frequency. At resonant frequency it is a 50 ohm here, this feed line is 50 ohm, source is 50 ohm, all are matched, maximum we will be getting. But here the impedance of the antenna at this position edge changes as a function of frequency. At 2.4 gigahertz impedance here is 50 ohm. So at that frequency this line is 50 ohm, this source is 50 ohm, everything is matched, you will be getting maximum radiation. But as the frequency deviates, the impedance at the ear changes here. So automatically that is the impedance changes means it deviates from 50 ohm. Reflection start because mismatch will occur. So that impedance, whether there is a matching at what frequency this impedance become 50 ohm. Okay, that we can study from the Smith chart plot here. So this is the impedance plot, this is a Smith chart. Using a Smith chart we can plot the input impedance here, that is Z11 here, Z11 we can plot as a function of frequency. You see here, this is a red color circle here shows impedance, frequency variation, at a frequency, see at this particular frequency it is center of the Smith chart. Center of the Smith chart means up to 2.387 gigahertz. Okay, that is at resonant frequency. You can observe impedance on the Smith chart. It is R is equal to 1. See here, R is equal to 1 and X is equal to 0.005. 0.005. X is almost to 0. Okay, and real part is equal to 1 at this position. At what frequency? At is 2.387. That means at resonant frequency. So at the resonant frequency R is equal to 1, that means center 50 ohm, normalized impedance is 50 ohm. 50 ohm means it is a matched one. So if you, this is the frequency variation, if you move like this frequency changes, and all those frequencies impedance changes, R and X value changes. We can observe that by moving this marker we can observe the impedance here varies here as you move over for different frequencies. Only at the resonant frequency we can observe R takes the value 1 and X is a 0 approximately. So that is a matched one. So like we can observe by drawing this graph, that is impedance plot. By plotting the impedance, input impedance on the Smith chart, we can at the resonant frequency we should have this value, that is R must be equal to 1, X must be equal to 0. That is satisfying from the plot here. Okay, at this particular position it is coinciding. At a 2.38 the plot is coinciding with the 1, so it is a 50 ohm. So at that frequency the impedance is 50 ohm, so it is a maximum radiation is there, maximum power is delivered to the antenna. So in the lab simulation tool we should plot this and we have to observe this, and also we should plot this and we have to observe. Okay, so these two plots as a function of frequency, see like this we have to rather frequency as a function of frequency. In the simulation tool you can do this. So here in the AWR tool, so this I have drawn already, this structure I have drawn. I have given here how to draw the structure. So this is here how to draw the structure I have stated here. This is the slide. If you go through this slide you can come to know how to draw the structure in the AWR tool. So I am not drawing this structure, all this I am not following in the simulation tool. I have already you can follow these figures and you can draw the structure in the simulation tool. So this is a structure you can draw in the simulation tool using those steps. Okay, So here we have to add a port 1 to the edge here, that is a feed line here. So feed line we have to attach the port here. So it is a one port device, you cannot add one more port. Okay, only one port you have to put like this. Okay, so now what we have to do, we have to plot S11 and the impedance Z11. So these two you should plot here. uh, so to plot this reflection coefficient and this impedance plot here, what we have to do, you go to the antenna here, add graph here, graph, and before that we will set a frequency. We will set here 2.2 gigahertz to 2.6 gigahertz. Okay, so that is in the step size of 0.01 or 0.001, also you can give a lesser number of points. So this is a one here. Okay, so similarly here also you better have to change in the. So apply here, we'll be getting this, it's okay. Okay, so now you have to add the graph to get a S11. It is a rectangular plot and create here. Okay, so this and add measurement here, go to this add measurement, and here S11 we are plotting only S11. So it is from this antenna 1, so I am taking antenna 1, you put, and it should be dB and magnitude here, add. Okay, close here. Now you have to so here we have, I have no frequency in gigahertz. Okay, so now we have to simulate this. So here one more thing is, it's a zero point 0.5 and zero point 0.5 we have to take, and remaining I have set here substrate zero point 0.5, material is 0.01, and here air is a 30 here, and the material is 2.2, and it is a 59 here. So this is okay here. Okay, and one more thing here you have to see here, in the axim here, this should be enabled, this and this both should be enabled here. Okay, and then you have to simulate. Okay, I will change this the point 1. So this is a graph here, what we are observing. So we will be getting this graph. This is a S11 plot, or we can can optimize this by putting a 0 apply. We will be getting a smooth curve we can get. by taking 0 1 apply. Okay, you can do this. So what we can observe, this is a smooth curve we can get, so it is resonating at this frequency. So maximum radiation we will be getting at this frequency, that is 2.39 gigahertz. We got a maximum minimum reflection, so maximum radiation, this is S11 flat, and minus 25.9 dB we got here. So this is we have to observe here. Next, one more graph what we have to do. So minimum reflection is there at the resonant frequency, and one more graph you have to add, that is the input impedance plot, that is the Smith chart here. Smith chart create here, and you should add a measurement here, add measurement. In the add measurement, it is a Z parameter input, Z we have to plot, and this is a 1 here. So it is a complex, so add and it is a close here, simulate again. So we will be getting this flat here. So what we can observe here, at the resonant frequency, odd marker here. See, you can add marker here. So from the marker we can see it is 2.32. We are getting it is 2.388 is a frequency at that, and you can see here up to 2.39, that is where it is resonating. The antenna is resonating at 2.39 gigahertz. At that frequency R is equal to 1.04 and X is equal to approximately 0.08. So X must be 0 and R is 1, it means 50 ohm here. On the Smith chart it is 1, normalized is 1, so it is 50 ohm. So at a resonant frequency 2.39 we are getting a 50 ohm, that's why it is radiating. But as you move like this, you see frequency changes. 2.39 we can see here it is R is 1.7, 1.7, X increases here. See, like this frequency increases, X value and R value changes, R value, X value changes. That's why impedance changes here at the here at this point. The impedance changes here only at 2.39 gigahertz, that is a resonant frequency. We will be having 50 ohm. We to 2.39 the impedance is a 50 ohm, that's why the reflection is very less here. Okay, that we can observe here. As the frequency deviates, that is 2.4 gigahertz, R value is 2.3, that is not 50 ohm. So automatically there is a mismatch here, mismatch happens here, that's why reflection will be there. Okay, so that you can test from this Smith S11 plot, the Z11 plot, that is the impedance plot. So at a resonant frequency at a 2.39 we have this matching will be there. This is a marker, you can bring it you can observe here 2.39 exactly, you will be getting 1 here. Okay, so like this you can check impedance plot. So these two plots we have to plot as a function of frequency. See, like this and this we have to plot for the antenna. Next is we should see whether it is radiate. Okay, energy is transferred, maximum power is transferred to the antenna. So from this and this graph what we come to know, maximum power is transferred to the antenna. Okay, to 2.39 gigahertz maximum power is transferred to the antenna, but whether it is radiating or not, that we should come to know. Okay, and also we have to know what is the gain of the antenna, that we have to test. And also, as I told, current distribution will be like this. This is the current distribution. Current is maximum at the center and it is minimum at either side. This happens at the resonant frequency, this will happen at the resonant frequency. So that we have to test whether current is minimum here and here, maximum at the center at the resonant frequency. That is resonant frequency means we got already this, that is at 2.39 gigahertz. 2.39 gigahertz we got a resonance from the one. So, okay, and we have to check whether the current distribution is maximum at the center and minimum at the edges, that we have to check, that we can check in the simulation tool. And also we have to test a radiation pattern. Okay, so the radiation pattern we have to, so current distribution will be like this. That is, if you once we simulate it, you can observe current distribution will be like this. Okay, current is maximum at the center here. See, from this bar you can see this is a maximum. It indicates a bar graph is there. This maximum is this, and the color blue color is the minimum here. So what we can observe here, blue is at the edges here, that is a minimum current. Here and here minimum current will be there, and this is a maximum value of current, this orange color. So as you can observe, it is maximum at the center here, and this plot you can observe only at this f0 equal to 2.39 gigahertz, because at that frequency the antenna radiates maximum. Okay, so the current distribution will be like this. But if you plot this same current distribution at other frequencies maybe other frequencies means somewhere here, this is the antenna is not radiating at all at this frequency and at this frequency. If you plot at those frequencies, you can observe current may be minimum at the center. That means you can observe blue color at the center of this one. Okay, so what we have to do, we have to observe this is a 3D plot of the antenna, inside fed antenna. So if you plot this in the 3D, you will be observing like this, and current distribution you can observe like this at a 2.39, that is at single frequency we have to plot it, 2.39 gigahertz. Okay, this is current distribution, and we have to plot a radiation pattern. So this is a radiation 3D pattern. So antenna radiates maximum in this direction, that is antenna is thickness is in the z direction here, and width is in the y direction. This is y direction, this is y direction, width is in the y direction, and length is in the x direction. This is the length is in the x direction, and width is in the y direction, and thickness of the antenna is in the z direction, and maximum radiation is along the z direction. See like this, we can observe bar graph again. So this is red color represents maximum radiation here, and you can see in other directions, see here, and other directions amplitude reduces here, radiation reduces. This is a field distribution, far field e total. What we are plotting here, e total we are plotting radiation pattern. So this is e total 6.67 at the along the z axis. Okay, along the z axis the antenna center is along the z axis. See, as you can see here, antenna center or that is in the we can have at the center, this is z axis is there, or so along that center, from the center it radiates maximum. See like this. Okay, so using this color graph you can identify what is the maximum value. So here you can get 6.68 in this range. So this radiation pattern, 3D pattern, we have to plot, and also we should plot these 2D plots. 2D plots means by taking cross sections. See like this. See, these are the cross section. This is a 3D pattern here, and x direction and y direction and z directions are this, y, x and z directions here. So this is in the spherical coordinate system we have to plot this spherical coordinate. Actually the antenna plot must be in the spherical coordinate system. Instead of x, y, z, we say pi, theta variation and r variation. So this is the pi direction. Encircling the antenna is the surrounding the z axis. Surrounding z axis is the, this is blue color. Surrounding z axis, that is a pi variation. You see like this, pi varies along this blue color. Okay, cross section if you take, this is a pi variation, and theta variation is like this. See like the z axis. Z axis, from the z axis if you deviate like this, that gives the theta variation. Theta, this is also theta variation. Vertical plane. See this red color one, if you take a cross section over this red color circle is there. If you take a cross section over this, that is theta variation. Pi is constant, because we are taking cross section at theta pi 90 degree. Along y direction, pi is equal to 90 degree. So we are taking a cross section of this at pi is equal to 90 degree. If you do take a cross section and if you observe, it will be looking like this. You see, the pattern may look like this. 2D pattern. This is called as 2D pattern. This is a 3D pattern. Okay, if you take a cross section, for example, along this red circle, you take a cross section and observe it from the front. Along the y axis, we are taking cross section. Theta varies here, theta varied, but pi is 90 degree. If you take a cross section, it may observe like this. Okay, similarly we can take here also. This is a theta variation. Again theta varies like this, theta varies here. Okay, vertical cross section, again it is vertical cross section, means theta varies, but it is 90 degree with respect to this red line, red plane. This is a red plane, this is a green plane. Here what we are both in this red plane as well as green plane, theta varies, theta varies, pi constant. Okay, in this for red one we are taking along the y-axis, pi is 90 degree, and here green one again theta varies, but pi is 0 degree. Yeah, from the x-axis 5 start, x is equal to 0 along the pi is equal to 0 along the x-axis. This is a x-axis, pi is equal to 0 along the x-axis. So this plane green circle is there. If you take a cross section along the green circle, there pi is equal to 0 degree here, but theta varies here. Okay, if you take over this circle, again the radiation pattern, see I have taken theta varied, pi 0 degree. That is a blue color one what we are observing here. This is a blue color one, the cross section in 2D pattern. Similarly, if you take a pi 90 degree, pi 90 degree means along the y-axis. If you take a cross section, again it is a vertical one, theta only varied. Again because it is like a symmetric pattern, either you cut along the in this green color one, or in the red color plane, approximately the shape of the pattern remains the same. So you can see here this red color pattern and this blue color pattern, only the width is different, but the shape remains the same here. Okay, that is theta, pi is 90 degree. If you take a cross section along along the y-axis, if you take along the x-axis, x-axis means pi is 0 degree. If you take a cross section, vertical cross section along the y-axis, pi is 90 degree. Okay, so like vertical cross sections along keeping pi 0 or pi 90 degree, by varying the theta, we will be observing these two floods, this red color one and a blue color one. Both are same, shape is same, only the width is different. From the blue one has a more width compared to the red one. Because of this is a small variation is there in the with respect to symmetry, not exactly symmetrical in the z direction, in the pi direction. Okay, so that is theta variation, and theta variation pi kept constant. So if you take a cross section, because we cannot draw it under 2D plane, that's why we take a cross section of this, and we are plotting. If you take a cross section like this, for different values, theta varied pi constant, that is vertical cross section, we will be having plots like this. Okay, in the bottom there is no radiation. You see, this is the antenna, it radiates only above here, above only it radiates, below there is no radiation. That's why xy plane, below the xy plane there is no radiation, only above the xy plane we have a radiation, and maximum radiation is along the z direction. Okay, and it is symmetric way about the z direction. We will be having approximately similar shape. If you cut here or in the 90 degree, these two planes are 90 degree with respect to each other. This red color one, green color one planes, they are 90 degree with respect to each other. If you take in either of this direction or this direction, we will be having the same pattern like this. Okay, so that 2D cross section we have to plot. Similarly, we can do the cross section perpendicular to this, that is in the pi plane also, pi plane. So that is in the blue see, this is the blue color circle is there, that is cutting this at the center. Okay, pi varies, but theta constant. See, these are the plots, pi varied, and theta constant here. Theta 0 degree, so, and here if you plot somewhere here, theta 0 degree, theta 45 degree, theta 45 degree, you cut it here. or theta 30 degree, and this is for theta 45 degree. See, like this, theta 45 degree, but cutting horizontally, not vertical cut, cutting horizontally. That is pi variation. If you cut the radiation pattern horizontally, that is the pi variation. Theta remains the constant. Vertical cross section, theta varied, pi remains constant. Okay, so for different values of theta, if you take a horizontal cross section, theta 0 degree, theta 45 degree, theta 30 degree, cut horizontally, we will be observing this circle. See, this pi is varied, theta 0 degree, we will be having this circle that is at the top, we are cutting here. Similarly, it pi is equal to 45 degree, this one, see, this is pi is equal to 45 degree. Okay, so here this is the angle here. Here is a angle, here is a 0 degree. This is along the z-axis. Along the z-axis, 0 degree here, 0 degree, and 10 degree, 20 degree, 30 degree, like this it deviates. So z-axis, along the z-axis, it is 0 degree, and as we move like this, the theta varies here. Theta varies as we move from here. Theta varies. Theta is 10 degree, 20 degree, and along the x-axis it is 90 degree. So if you come here, this is 90 degree here, 0 here, 0 degree here, it is 90 degree here. Similarly, this side also, this is minus 10, 20, 30 degree, like this, and 90 degree again here. Okay, so like that, this is a theta variation for these plots, uh, theta plane plot and pi plane plots. Okay, and for this pi variation, the same values indicates pi variation. See, like this. Okay, that we will see how to plot this 3D pattern. We will see how to plot this in the simulation tool. See, to draw the radiation pattern, this one, actually this radiation pattern must be drawn only at a particular frequency, that is at 2.39 gigahertz. So we will plot the radiation pattern, 3D pattern, and current distribution at resonant frequency. We can also plot here and here also. Okay, if you want to see radiation at different frequencies, you can plot at this frequency, you can come to know what happens to the radiation pattern if you plot at different frequencies other than resonant frequency. Okay, first we will plot it at 2.3 gigahertz, 2.39 gigahertz, and we will see that. Okay, so to do that, so in the simulation tool here, what we have to do to draw the first, we will see this current distribution. Okay, so the current distribution we will plot first. So what is the current distribution? Is current distribution must be maximum at the center and minimum at the edges here. That plot must come. Okay, so here to do that, one what we have to do, see, in this structure, we should change the frequency here, because it is only at a resonant frequency, that is we got at 39 gigahertz. So single frequency apply, only 2.39 gigahertz. Okay, similarly here also we should change, that is again 2.9 gigahertz apply. Okay, okay, so now here what we have to do, one to see the current distribution, you should add this annotation. So there is a, see, this symbol is there, you click over that em annotation, you have to click over that, this window will appear. Okay, em annotation, what you have to do to get the current distribution, you should go to here, this em annotation, you click over that, this window will appear. Here what you have to do, planar em, only you have to keep planar em, but you should take em current here, em current, that is antenna 1 only, and you should choose here in dB. Okay, and you change it to 40 here, this is a 40 here, and the frequency we should choose, this is 2.39 gigahertz. Okay, so this have to choose, and then apply. Okay, so this annotation will appear here. See, below this information, this is a antenna one what we have created. This was not there. By adding this annotation we will be getting this. Okay, so now again here one more thing what we have to do, again we have to go here. Okay, properties, you should change, go to the properties, go to annotation. See, what we did, go to annotation, properties here. What we did here, EM plane, you take a EM current here, antenna, and you changed it to 40 dB you have taken here, and the frequency is this, and here you can close it here. Okay, this is a okay. So now what we have to do here, you should go to here options are there. See, in the antenna you should go to options, there axim is there. You see here, you should go to axim. Here you should uncheck this, enable AFS, enable AFS. Okay, that you have to do, then it is a okay. Okay, now you simulate again. Okay, now to see the current distribution, you should go to here, 3D plot, 3D only you have to go to 3D. This is 2D what we have, 3D you should go. Okay, so this color you will be observing this. You see here, you can rotate this, you can see here. But what we did is at 2.3 gigahertz we plotted, and you can see here current is maximum. This is representing maximum current, and this is a minimum current. So as we expected, minimum current must be at the edges here. Okay, so that is blue color must come here, and here is a blue color here. So at the center there is a maximum current here, maximum current. So this it is a center, orange color is there at the center here. So like this, this is a graph we have to observe in the laboratory. It says a current distribution should be minimum at the edges, and it is maximum at the center. Thus, so this graph you should observe in the one. Okay, so after this what we have to do, okay, this is a current. Next you should see the 3D pattern. So you should see this 3D pattern here, this one. To see the 3D pattern, what we have to do in the simulation tool, see here in the simulation tool, again you go to here, okay, here in the properties, here is the antenna. Okay, this is the antenna 3D. See here what you have to do, you go to 3D rotation only. Okay, their properties, their antenna you should take, their antenna 3D. Okay, antenna 3D, include losses, you should say include losses. Okay, and you make it 10. This is a 10 here. Okay, in dB only, and this is frequency select tuner, it is at a 2.39 gigahertz only what we wanted is. Okay, so then you say okay. Okay, then you simulate again. Okay, one more changes you have to do, what you have to do is go to options here. Okay, here axim again. See, this also you should uncheck here, should also uncheck. See, to get the current distribution, this is unchecked, this should be checked. To get the radiation pattern, this also should be unchecked. See, like this. So what you have to do, you should go here, options, there axim is there. See here axim, in the axim AFS and this both this one and this one both should be unchecked. This that is enable de-embedding, that should be unchecked, and enable AFS also must be unchecked. But for current distribution, this should be checked, this should be unchecked. Okay, so okay here. Now again you simulate it. Okay, one more, I did a wrong thing, one more what we have to do here, here one more setting we have to do, properties, polarization. You see here, polarization, here in the polarization you should take total, you should take a total here, total. I have not done this 3D antenna. Your structure name here, losses should be included, and this is 10 dB and it is in dB. This should be 2.39 resonant frequency, and this should be total here. You see here, total polarization should be total. Okay, so it is okay here. Again you simulate this. Okay, so you will be getting this. See, this is the radiation pattern here. So this is what we have got, a 3D pattern. This is the radiation pattern, 3D pattern, what we are observing here. So this see this we can make it this is looking wider here. This is wider. You can make it by taking different, see here, instead of go to properties, if you change it, see for example 5, if I take it 5, what will observe, you see it will be looking like this. Okay, so to see the better features, you keep it as a 10. Okay, so and okay, so it is looking like this. Okay, you can see here how does it look in the bottom. You see here it is radiating only above. The structure radiates only above here, above the you see there is in the bottom there is no radiation because copper is there. Okay, and here you can observe maximum is along the z-axis. This is a maximum. Color bar is it is a green is coming here. Maximum value is the green here, that is 6.65 here. This is a color bar. Wherever green is there, that is a maximum radiation. Green color is a maximum radiation, blue is a minimum radiation. Here orange is a medium radiation. So 6.65 is a maximum radiation, that is along the z-axis here. Okay, we will be having like this. So if you this is a radiation 3D pattern you're supposed to get from the one. So what we can do now, we will be taking cross section of this. See, if you take vertical cross section, you cut it vertically or cut horizontally. Cut like this, this is a horizontal cut. Okay, if you cut it vertically like this, vertically again there are different directions. Vertically like this you can cut, vertically like this, vertically like this you can cut. So along the vertical cut here, if you do see this here like this, if you take a cross section, I have 3D pattern we got now. This is a 3D pattern. So this is a 3D pattern what we are having. This is a 3D pattern. So this is a 3D pattern. To take a cross sections, what we have to do here, 2D, this is a 2D graph of the antenna pattern. To get this 2D pattern in the different planes, different plane means in the vertical planes. In the vertical plane means theta varied, pi constant. See, pi constant at 0 degree, pi constant at 90 degree, theta varied, that means it is a vertical cross section. Okay, the shape of the pattern looks like this. If you take a vertical cross section, see like this, near 0 degree and 90 degree. If you take a horizontal cross section, pi varied, theta constant. Okay, so now we will see this how this plot is in the simulation tool. So to do that, the 2D pattern, to take a cross section, either vertical cross section, see, cut a vertically or take a horizontal cross section. Vertical cross section means theta varied, pi constant. Horizontal cross section means pi varied, theta constant. See, from this graph what you can see, if you cut horizontally, the pattern is looking like a circle only. If you cut it horizontally, see like this, if you take a horizontal cross section, because it is like this, see the shape is like this. If you take a cross section of this, automatically the cross section will be like this, horizontal. This is a horizontal cross section, will be like this. It is looking like a circle, see like this. Okay, as you go to the bottom of this, see, as you go to in the top, almost looking like a circle. If you take horizontal cross section here almost looks like a circle, but at the bottom, you see, as we can see here, this is a radiation reduces here. Okay, if you take at the bottom the cross section, then what happens, it may be looking like this. You see, the shape will be going like this, it is becoming like this. Okay, it may become like a figure 8 at a very bottom. If you take at a very low, see like low values of theta, we'll be getting, it looks like a figure 8. See, it is looking like a figure 8 here at the bottom if you take a cross section, horizontal cross section, but at the top almost it looks like a circle here. So now we will see how to take a cross section in the vertical plane. Okay, to do that you should add the graph. You go to graph, new graph. Okay, but here you should take antenna plot. It is a create here. Okay, so this plot will come. So now here, see, this is a graph here. You should add your measurement graph 3, add measurement. So again here, what we have to do here, see here you should go to here electromagnetic, here electromagnetic, under that antenna, see under that, see it is like this. Okay, it will be like this. What you have to do, you should go to electromagnetic, there antenna, see it will be like this. You should click here antenna, there you should see sweep by or sweep theta, as we see vertical cross section, see here vertical cross section. What we are doing, we are varying theta, keeping pi constant. So in the simulation 2, what we have to do, sweep theta. Okay, and we should plot e total. This is a total we have to choose. Sweep theta, vertical cross section we are doing, this is a 1, include losses. Okay, and pi 0 degree or 90 degree, as we can see, theta varied pi 0 degree or theta varied pi 90 degree. So I am taking first this one, theta varied pi 0 degree. Okay, for that blue color one, you see this is a blue color graph what we got. Okay, so that here, so here is what, pi 0 degree, theta varied. Theta varies from 0 to 180 degree, this direction 0 to 180 degree here. Okay, use 2 degrees sweep angle for theta varies here. At what angle it varies, with a variation of 2 degrees. Okay, and it is magnitude, and this is dB, add here. Okay, close. So you will be getting this. Okay, so here this in the plot, you can, this is a 2D pattern cross section. You go to action, see here actually this is a very low minimum value it has taken to plot. What you have to do, you go to here grid. Okay, here auto limit, that is, you see here -40 to 10 dB. Actually maximum gain we got 6.6, so you start from 0 dB and maximum is 8 is enough. Okay, so you apply here, so you will be getting this. So this is the plot. So what we can see here is this, see graph here we have that is pi is, see here pi 90 degree. Okay, and you can see in this graph there is a color, this is there, see here graph options, you can see here grid. Okay, you can see format. Okay, here you can change it to some gray color, the apply, you can see here this is the angle here, and the fonts you can change font here axis numbers. Okay, it is bold, you can take silver, instead of silver you can take a black here, you can 14 you can take. Okay, apply. So you can see here this is an angle 0 degree along the x-axis, this is a x-axis 0 degree, sorry, z-axis, along the z-axis 0 degree, 10 20 30, theta varies, theta is varied like this. See theta varied, it is up to 180 degree, and here -10 and it is up to 180 degree, -180 degree, because theta, as you can see here in the 3D plot, see here theta this way and also this way. Okay, this is starting from here 0 here along the z-axis. Theta, if you go like this, it is 90 degree here 90 degree, below that it is 180. Similarly here below this structure there is a, this is 90 degree here, below that comes a this one, see what you can observe here, up to this 90 what we have here. see this up to 90, this point is this, okay, 90 degree. Below the structure is this, below the structure there is no radiation because copper is there. Okay, so maximum radiation we got here at the z-axis, along the z-axis, that is theta is 0 along the z-axis, theta is 0. Here we got a maximum. What is the maximum radiation? You can see that, you see here marker, odd marker, you put it here. See, it is 6.65 maximum radiation you are getting in decibel gain of the antenna. It is a gain, far field gain 6.65 dB maximum value we have radiation gain of the antenna, or it is a E total. Okay, we are plotting, and that is at 2.39 gigahertz, and it is 0 degree, approximately at 0 degree we got a maximum gain here. Okay, and the gain reduces as you go in a different direction. You see here gain in different angle, this is angle variation. You can see gain decreases like this. You see here gain is at 31 degree, 31 degree. What is the gain value? 5.29. gain reduces in different angles. See, when theta is 0 degree we have a maximum gain, but as the theta decreases, you see here theta is for example, if you go theta is equal to something here. Here you see at theta equal to 48 degree, theta 48 degree. See, this is a 48 degree. See, this is a 48 degree here, around 48 degree. What we have, the gain is equal to 3.62, 3.62 gain of the antenna. Okay, okay, so like that, and similarly gain varies as the theta varies, gain varies, doesn't remain same. Gain is maximum here, and theta, as the theta varies, the gain changes. At 48 degree, theta is 48 degree, we have gain is equal to 3.6. Similarly, if you go down, you see theta is, what is the theta value here? 90 degree, 76 degree, approximately 0 dB. So here along 90 degree it will be 0. Okay, so like that gain reduces, and we can find out half hour points. Half hour point means you find out the direction at which the gain is half of the maximum value. This is maximum 6.6 dB, 3 dB down from here, that is 3.6 dB approximately. You go come to the direction at which gain is 3.6. you see 3.6 dB. Okay, it is in which direction? That is in 48.42 degrees. Okay, this is a half hour point. Because it is in decibels, 3 dB down from the maximum is the half hour point. So in which direction that half hour point is? At 48 degree. Okay, similarly by doing like this, and add one more marker here, and that is here again that side also 3.6 here. See, 3.6 here. Okay, 3 dB down from maximum value, it is minus 48 degree, it is a plus 48. So from this you can find out the beam width, 3 dB beam width, 3 dB beam, half hour beam width. Half hour beam width, you know how, what is the definition of our half hour point? See, like this. See this from this half hour point. Half hour point means from the center of the maximum direction you go in to the direction at which gain is half of the maximum value. So this is maximum, half of the maximum value is here. Similarly half of the maximum value is here. Okay, so you take a angle value here, angle value here, total angle you find out from here to here, that is the half hour beam width. So half hour beam width is here 48 degree approximately, here it is a 48 degree, totally 97 degrees. From here to here total angle is 97 degrees, so that is the half hour beam width. Okay, so like that you can find out the half hour beam width. So here what we did here in the AWR tool, we have taken a cross section. We have taken a cross section of this, from that cross section 2D. You can if you take a cross section of this, if you take a cross section, vertical cross section, that is pi is 0, theta varied, the graph is like this. It's a maximum value. See here maximum value is 6 here. This is maximum value 6 dB is 6.6. So what we got here, maximum is a 6.6 here. from the marker we got here, it is a 6.6 dB. Okay. And this is a gain reduces in either direction. If you move theta, gain reduces, and take up directions at which gain is half of maximum value, here and here. Find out the total angle from here to here. Okay, 48, and this is 48, 100 and sorry, 97, nearly 96 or 97 degrees you will be getting from here to here. That is called as half hour beam width. Okay, you know that in the theory what is a half hour beam width, why it is necessary to find all those things. So in the 2D plot you can do that half hour point similar to this. So this is I have done for which values here, 2D plot properties. What I did, 0 pi 0 degree I got like this, pi 0 degree, this is a flat. Okay, that is theta varied pi 0 degree, I got this plot. Similarly I can take here theta 90 degree. Okay, theta 90 degree, and apply. Sorry, okay, you will be getting like this. You can add here, add both also you can add. There is a add option is there. This is the theta. Okay, 90 degree, and so okay, okay, here only you can add 90 degree, you will be getting this. Okay, again this is for theta is 90 degrees. See here, pi 90 degree, pi 90 degree the plot is like this. Or you can graph 3, you can add that also, add measurement here, add measurement 90 degree we have already, this add 0 degree also, 0 degree add here. Okay, you will be getting like both. So what is this, theta 90 pi 90 degree, this is the one blue color one. Pi 0 degree we have this red color one. So these are the plots. Okay, cross section when you take along the this x direction, and see from here, if you take along this plane, red color plane, that is pi is 90 degree. If you take a cross section along this green color one, that is pi is equal to 0. Okay, the plots are like this and this, blue color one, red color one. So that what we are observing here, blue color one and red color one for pi 90 degree and pi 0 degree here, theta varied. Okay, so this is a theta, this is a theta here, and you see here circles are here, this is actually gain circles, gain circle starting from 0 dB. See here the 2 dB per division. Okay, minimum value 0 dB. See, this is a minimum 0 dB here, and here the value is 2 dB. This is this circle, this circle is 2 dB circle, and this circle is 4 dB circle, this circle is 6 dB circle. Okay, see like that. So here 2 dB per division. If you move like this, this is 2 dB per division, this is 2 dB, 4 dB and 6 dB circles. If you take any value here over this circle, it is 6 dB. Similarly here it is a 2 dB, sorry 4 dB, and this is a 2 dB circle. Here is a 0 dB starting from minimum 0, maximum is 8 dB, this is 6 dB, this is a 8 dB circle, this is a 8 dB circle. You can change a number of divisions also. See, go to options here, I took here grid maximum as 8. If we take if I take 10, what we get, see apply, see this is now 10, this is 10, again 2 dB per division, this is 2 dB, 4 dB, 6 dB, 8 dB, 10 dB. Okay, because our gain itself is 6.6, I have taken this is equal to 8. Okay, apply and so like this you can draw. So this is for pi theta variation, pi constant. You can find out beam width for each of these, this also you can find out beam width, for this also you can find out beam width, and you can draw this what is that, here cross section, horizontal cross section. So you can take a horizontal cross section. If you take horizontal cross section means pi varied, theta remains constant. So we will add that graph also here, add. What we have to do here is a pi sweep pi. Okay, and total only we have to take, include losses here. Theta 0 degree, instead of 0 degree I am taking this as a 30 degree. Okay, you can take 0 degree and you can see also. this is odd here. Okay, okay, this is a close, you can simulate here. You see here, this circle comes here, pi varied, this now, this for this circle, this is pi varied. See, pi varied theta 30 degree, theta 30 degree, pi varied, that means horizontal cross section, we are taking horizontal cut at theta equal to 30 degree. It looks like approximately circle, see, because it is like a circle only. If you take horizontal cross section of this, it looks like a circle. So that graph is a circle like this. This is a circle. Okay, and these values for this circle, that is this pattern, 2D pattern, theta 30 degree, these values are pi values, pi 0 along the x-axis here, 10 to these values corresponds to pi. Okay, for this plot, for these two plots, these values corresponds to theta, these values corresponds to angle theta values. For this okay, these values represents the pi variation, okay, you should not confuse. There are, we have plotted pi variation, theta variation, both in the same one. Okay, for if you consider this plot, this is a pi variation. In the pi variation, these values corresponds to pi, and here this blue color and pink color for theta variation. For theta variation, again these values corresponds to theta. Okay, pi constant. So like that, you can draw the cross section of this, you can draw the cross section of this in the horizontally, or you can draw vertically, you can cut, you can horizontally cut, you can see the radiation pattern like this. Okay, so this is about antenna. You can find out a beam width, as I said here in the plot. You can see, you can find the beam width, half or beam width, maximum you can find out maximum gain of the antenna, you can find, and you can draw this, you can do this, and also you can see the current distribution for this one. Okay, so this